Hello, course staff. My name is Zuleika Islam, recording from DG Khan, Punjab, Pakistan. My edX username is Zuleika Islam, and my GitHub username is Zuleika2006. Today, I will be presenting a technical analysis of a three-stage exploit chain targeting Seimens RuggedCom ROX2 operational technology switches, which was publicly disclosed by Unit 42 and Seimens. I chose this topic because operational technology devices, like substation network switches, are the backbone of critical physical infrastructure. This specific case study connects directly to our course topics on input sanitization, argument injection, privilege separation boundaries, and post-exploitation persistence. Rather than relying on a single critical vulnerability, this exploit demonstrates how an adversary chains low and medium severity logic defects together to achieve unauthenticated root remote code execution. To understand the severity of this failure, we must examine the role of ROX2 switches in operational technology networks. Unlike IT switches that simply route corporate web traffic, ROX2 appliances operate in harsh industrial environments, such as power substations and transportation hubs. They manage communications between human-machine interfaces, HMIs, SCADA servers, and industrial control devices like programmable logic controllers, PLCs. Because OT environments frequently rely on unencrypted legacy protocols like Modbus TCP or DNP3, network switches are trusted to enforce strict VLAN segmentation. A compromise of the switch management plane effectively breaks the physical isolation boundary of the entire industrial facility. Let's dissect Stage 1 of the exploit chain, tracked as CVE 2025-40948. The vulnerability lies in how the web server's JSON RPC interface handles file uploads and compression tasks. When processing a file request, the web server invokes the Linux XZ decompression utility using a privileged background daemon running as root. However, the software fails to sanitize command line flags and argument delimiters passed from the web request. By passing crafted flags directly to the XZ command execution string, an attacker forces the utility to read arbitrary files across the Linux file system. While marked as medium severity on its own, this allowed adversaries to dump sensitive system files, including shadow password hashes, network topology maps, and cryptographic keys, providing the exact intelligence required to construct Stage 2. Stage 2 represents the pivotal privilege escalation step, tracked as CVE 2025-40947. ROX2 includes a feature key mechanism designed to unlock optional software modules. During reverse engineering of the key validation binary, researchers discovered that the signature verification routine constructs an OS system command by concatenating user-supplied string data directly into a shell execution string, likely via functions like system or popen. Because the input validation routine fails to filter shell metacharacters, such as backticks, semicolons, or command substitutions, an attacker crafts a feature key containing an inline payload within the signature field. When the privileged verification process executes, the embedded command runs immediately under the root context, UID equals 0, giving the attacker complete control over the switch operating system. The final phase of the chain establishes permanent persistence. Having achieved root access, an adversary needs to ensure their access survives device reboots and network power cycles. The researchers identified a third flaw in the switch's system scheduling module. The web-based task scheduler failed to sanitize input before writing entries into the system cron configuration. By injecting malicious commands into scheduled task parameters, the underlying Linux cron daemon executes attacker-controlled payloads at regular intervals with full root privileges. This turns the switch into a persistent, self-healing entry point inside the industrial network. This incident highlights 3 fundamental software security principles covered in our course. First, command and argument injection. The reliance on shell-invoking functions like system without argument parametrization remains a primary vector for binary exploitation in embedded systems. Second, exploit chaining dynamics. Security evaluations cannot treat vulnerabilities in isolation. A medium-severity file disclosure provided the internal operational context needed to weaponize the high-severity command injection. Third, privilege separation deficiencies. The web interface components executed administrative utilities directly as root, rather than enforcing dropped privileges or sandboxed service accounts. To mitigate this threat and prevent similar embedded failures in the future, organizations and software developers should implement 4 core recommendations. First, parameterize system execution. Software developers must eliminate system and popen when interacting with OS utilities, replacing them with parameterized APIs, like exec-v, where arguments are passed as discrete array elements rather than interpreted shell strings. Second, enforce least privilege in web daemons. Web interface daemons must run under low-privileged accounts, web-data, and utilize granular privilege escalation policies, such as targeted pseudo-ers rules, rather than full root execution. Third, apply vendor patches. Asset owners must apply Seimens firmware version v2.17.1 to remediate all 3 CVEs. Fourth, isolate management interfaces. Management plane access, HTTP, HTTPS, SSH, should never be exposed to the primary data plane or industrial traffic networks. It must be restricted strictly to an out-of-band management VLAN. In summary, the Seimens ROX2 exploit chain illustrates how software design oversights in web interfaces can compromise physical critical infrastructure. By enforcing parameterized execution, strict input validation, and isolated management networks, we can protect embedded control systems against complex exploit chains. Thank you for your time and consideration.